Oh, yes, yes, please. Okay, so it's so nice to see everybody again. Even though even this week is the midterm week, and you're going to finish your project very soon, but I'm still going to introduce some idea about how to make a finite state machine. So, but before that, we have a news announced in our class board. It's over here in the iStudy system. So I just posted a new topic over here. We're going to postpone our due date of our midterm project. That is because there are too many typhoons in this year. So probably you'll need some more time to finish your midterm project. So we're going to postpone the delivery date. We're going to postpone the due date of our midterm project. Okay, so let's see the post content over here. I just upload a new version of our project requirements. So you may find the project requirement in the iStudy board. And please do be noticed that the due date is postponed. So the new due date will be November the 21st. Okay. So 1 week postponed. All right. And today we're going to introduce the chapter number 5. It's about how to make a finite state machine. So, but I was still going to upload the whole video to YouTube, just like before. So, if you are going to busy, you are going to focus in your midterm project right now, it's okay for me, and you can refer to the upload video later. All right. So let's start the class today. Okay, I know there are some missing parts in chapter number 4, but I'm planning to introduce the remaining part of chapter number 4 just right after the midterm project is uploaded, just right after the midterm project is over. Okay, because the missing parts are not so important to making the project for our midterm. So the missing part for our chapter number 4 is reflection and attribute. So for these two topics, we are going to introduce these two topics just right after midterm. Okay, so let's move on to chapter number 5. All right, okay, so today we're going to introduce the idea of finite state machine, in short, FSM. So it's a very, very well known, it's a very famous design pattern which will be utilized in game development. So if you are going to be a professional game developer, you have to know what it is a finite state machine. And besides that, the FSM, he has a brother, and the name of the brother is behavior tree. So probably you heard both of them. You heard FSM and you also heard of the behavior tree. So what's the difference between these two brothers? All right. So for me, I personally think these two brothers can do the same things in the game, like making an NPC, non-player character, or like making some game logic. And if you're going to implement some artificial intelligence, then you can choose any one of them. So both of the brothers, including the FSN and the behavior tree, they can make AI, the classic AI, not a deep learning one. Okay, so the artificial intelligence could be separated into two categories. The first category is classic AI, which is made of FSM, behavior tree, and some other similar algorithm. And the latest one is considered as deep learning model. So it's a little bit deeper topic for us to talk about in this semester. So probably next semester I'm going to have a new course. I'm going to open a new course, and the name of the course is Generative AI. So we are going to talk about the diffusion model and the transformer in the new course, which will be held in next semester. So in that course, I'm going to introduce what is deep learning, but not right now, not in this lesson. Okay, so so in this lesson, you'll learn. We are going to explore the concept of FSM, and we are going to understand their fundamental structure and behavior. So we're going to know the basic way, the basic mean to implement an AI system. And okay, so there are three important things to learn on the way of learning FSM. They are states, transitions, and events. So in order to design and implement an FSM, you are going to implement each of the three submodules. We're going to implement states, transitions, and events. So what are these three new things for us? Wait a moment, we're going to introduce later, right? So we're going to write C# code, and we are going to show you how to use UML diagrams to show the three designs. Okay, we're going to show how to use UML FSM diagram to introduce your idea and separate them to its states, transitions, and events. Okay. Uh, the way we're going to implement an FSM is called a state pattern. The state pattern is one of the many design patterns provided by the GAN04. Probably I had already introduced the book written by the GAN04. So it's the classic book in the design pattern and the software engineer industry. Okay, so we're going to introduce the state pattern later. All right. So, why this chapter is important? Of course, if you're going to make the AI for your character, then the easiest way you can choose is FSM. Okay, and in order to control the flow or control the game manager of a game, and the best way you can choose is also FSM. Okay. And besides that, if you write a larger game in the future, you'll find that your code will be a mess because there are too many logic stuffed into one C# file. So for complex game, the best policy for you is to separate different logic into separate files. But that is very difficult. How to do that? How to separate clearly between two C# files. So one means to separate logic is FSM. And by following the state pattern, you can clearly separate any logic you want into separate C# file. So that's the importance for software engineer, especially for game developer. Okay, let's move on. So in today's lesson, we're going to introduce two types of FSM. The first type is called the switch type FSM. And the next one is called the design pattern FSM. So for me, I was thinking that if you are a software engineer, then you have to learn the second one. But if you are a designer, including the visual designer, the interactive designer, or some visual art designer, then you only need to learn the switch type. Okay, if you are dedicated, you are devoted to learn software engineer, you must learn the design pattern. You must use design pattern to implement finite state machine. But on the other hand, if you are only interested in the visual part or the interactive part, then you may choose only learn the switch type. So for me, anything work, anything function is a good project. So I don't care which type you choose in your midterm project, but if you are going to choose the switch type to be utilized in your midterm project, then you may choose the project number one. As I can remember, the project number A in our midterm project is allowed to using the switch type FSM. But for the other, I think you'd better use design pattern for complex game. All right, let's move on. So before I write any code, I would like to introduce the idea about FSM diagram. So let's take a look over here. This is an example of an enemy finite state machine. So this is captured from the website over here. Here is a link, and here is the finite state machine. Okay, let me introduce the idea. Now we're going to implement an enemy. So for common enemy, he is wandering just all over the game world. So when he is in the wander mode, he always wander to any place he like. So this is wander mode. That means that his mind is in this mode of wandering. Okay, so when something happens to this enemy, he will switch his mind into another mode. So let's take a look at here. This is attack mode. So in attack mode, the enemy will try to attack anything he see or anything he found within his view. So this is attack mode. But let's take a look at the orange lines over here. The orange arrow means the transition condition for the enemy state. So let's take a look. When the enemy is wandering and the player is very near to the enemy, then the enemy will switch his mind into attack mode. So is it reasonable for you? Yeah, I think this is compatible with most of the experience in your gaming experience. When the enemy is sitting over there and you're going just toward him, and the closer you are, the enemy is has a higher possibility to stand up and fight back with you. So this is the sensing we had during our gaming experience. Yeah. But when the enemy is attacking and something happens, he will going to drop his attack stance and roll back to the wandering mode. So what would the event, what would the condition be? Let's take a look over here. So when the enemy is attacking, but the player is out of his sight, that means the player may be fleeing or escaping. So the enemy will turn back to wandering mode. So this is the loop between the enemy mode of wandering and attacking. This will form a loop. So let's take a look to the other state. So for this one, our enemy also have an evade state. That means the enemy is trying to escape. So let's take a look at the arrow over here. When the enemy is attacking, but the player is attacking back, oh, he is fighting back. So the enemy will change his mind into evade mode. Very smart, right? So when the enemy is evading, but the player is idle again, okay, then the enemy will come back and going to attack the player. A very smart guy, very smart enemy. So we see here, we see another loop over here again. So let's take a look at the state over here. So this state is called find aid. So when the enemy is in this state, he is going to find some aid. So let's see the transition condition. When the enemy is evading, but his health points are low, then he's going to find aid. Pretty reasonable. So when the enemy found some aid, Then he will switch back to the wandering mode. So this will form a very large loop over here. So inside this design of finite state machine, you will find a closed loop stable status and the transitions all around the diagram. So this is the design of our enemy AI. Okay, clear? So let's go back to the content over here. Definition. What is a finite state machine? A finite state machine is a computational model used to represent and control the behavior of an object that can exist in a finite number of states. Mr. Fu, you say finite, right? Are there any infinite state machine? Well, yes, there may be some infinite state machine, but it's not implementable. You'll never get you will never get an infinite things to be done. That is not possible. So the only doable way for a state machine is finite state machine. Even though you can make the number of states very very large, very enormous, but it is still a finite state machine. So that's the then why we call this kind of design a finite state machine. All right, so we are going to control the behavior of the object mhm, with a by the way of FSM. So the, in the diagram, we can find states in the rectangles. So within this rectangle, all the rules of the enemy's mind are described and written inside it. So we call this rectangle a state. So between two states, you can find some arrow, right? So the arrow line over here is called transition. The transition means the internal rules or conditions from moving one state to another. So this is transition. So Mr. Fu, what is event? Well, okay, for events, I mean external inputs or external triggers that will cause state transitions. So all the arrowhead over here is internal. Nothing is generated from external state. But if I can control the enemy with my controllers, like my PS3 controller or like my Xbox controller, then that is an external trigger to this system. So that kind of transition will be considered an event. But there are no clear boundary between transition and event. Sometimes I'm going to call a transition an event or vice versa. So these two terms could be exchangeable in some context. All right, but when I mean transition, I mean the condition is generated from internal system. And when I mean events, I'm going to mention about the input from external world, right? So when you can get the idea of an FSM design, you'll be able to utilize the FSM in game design, in AI system design, in user interface design, and in workflow automation. So we're going to demonstrate how we can utilize this idea in game development and AI system. For the user interface part, not going to talk about how to use FSM in UI in this lesson, but I'm going to show you how to use FSM to design UI in another courses. Uh, but that course is only available in Chinese language. So this is our application for the FSM. All right, next, let's have an example over here. We're going to make a ball. Actually, you had made this ball before. If you can remember, in your sophomore year, we are we were using the Bolt, the visual script editor. At that time, we designed an FSM bulb. So in this semester, we're going to do the same thing, but with C Sharp and the FSM. All right, so I think we can jump to the next slide. Right, this is it. So this is the first version of our finance state machine of a bulb. We have two states. Of course, we have the first state we have is on state, which means the bulb is on. And the other state is called off, which means the bulb is off. So when the bulb is in on state, the bulb is lighting and emitting some light into the world. And on the other hand, if the bulb is in off state, the bulb will turn off its light and you won't see any light emitting from this bulb. So simple, right? So let's discuss about Mr. Wu. When should the transition happen? What is the condition? All right, I will see. I will see that when somebody is touching the bulb, I would like the bulb to turn its state from on to off. So on the other hand, when the bulb is in off state and somebody is touching with his hand, for me, I'm touching this bulb with my finger, and this gesture will turn the bulb from off to on. So with the help of touching the bulb, you can switch the states in this finance state machine. Yeah, simple, right? So we see states, and we see transition, and we see events. Mhm. So let's go back to the context over here. Design a FSM state diagram for your device. So we had a device, we had to finish the design of our FSM. And we see the state, we see the transition, and we see the events. Pretty cool. Okay, next. Okay, so before we start to write any code, we have to make a bulb in our Unity 3D. So by following the procedure over here, we can get a bulb. And I just upload the model into our iStudy server. So let's take a look. Okay. It's over here. If you log into iStudy, and you can see there is a resources part of the class materials, and you can find chapter number 5 resources. It's a zip file. So by clicking the button over here, you'll be able to download resources underscore 05.zip. And within that zip file, you'll see one FBX model only. And that model is a bulb. So when you get a download and extracted model, you may be able to import the model into the Unity editor like this. All right, so by following the 1, 2, 3, 4 steps, we can finish the design of a bulb. So the first thing is to import the model into the scene. So let's import and drag a model into the scene. And now this one, this one. Wow, that is too big. You can see that the model is is uh, is making too big because it is amplified for 100 times in scale. So let's turn the scale back to 5, 5, and 5. Okay, now it looks better. And the second thing to tweak is that the model doesn't the, the model, the gain object, doesn't contain any collider. So we have to place some collider on it in order to sense the clicking or touching event from user. So how to add a collider for it? It's very simple. Um, by checking the import settings over here, so let's select the bulb model over here, and let's go to the inspector and find the model tab over here. So look, here are so many importing settings, and the one we are caring about is the generate colliders over here. So please check the option which is generate colliders for me. And after you check the generate colliders, please do remember to scroll down and find the apply button and click it. All right, so if you do this, it will generate a collider, and the collider will be placed onto the gain object in the world. Oh, it's over here, the mesh collider. So without checking the option, this mesh collider will not be shown. And you can find that some material is not correct. That is because we have to extract the material from the model. So select the bubble again and check the import setting. So this time we are going to do something in the materials tab. Let's switch to the materials tab. And we know that like Blender, like Maya, like 3ds Max, these are 3D modeling tools, right? We can set the material for a model within this 3D modeling tool. But once you export the model into some format like FBS or OBJ, the material setting is still over there. But your new software like Unity may not be able to automatically fetch the information within the 3D model file. So sometimes you have to set the game engine or other 3D software within some special settings over here, like this one. So we can see under the materials tab, there is a this one, location. And I think there are two more buttons over here. The first button is called the extract textures, and the second button is called the extract materials. What are these buttons? All right, actually, FBS file could also import or holding some texture within the file. So we have to extract the texture within the FBS before you use the textures. But for the simple bulb, there isn't any textures embedded in this file. So the button is grayed out. There isn't any texture in this FBS file. No. And you can click the extract material. And once you click the extract materials, the engine will analyze how many materials are written in this FBS file and extract the information and make it a Unity material for you. So I just click this button, so now my button is grayed out again. But for you, I think you can click the extract material button, right? So after you do that, you'll get two materials. One should be named as metal and the other should be named as glass, right? All right, so we have two different materials and we can change the settings and parameters within the materials. Great. So that finished the third step over here. So let's come to the last step over here. So we're going to add a ball game object to the scene, and we're going to add a light inside the ball. So by right click on the ball within the scene, you'll be able to find the light category. And in the category, you can find a point light. So this is what we need. Just add a point light over here. So we're going to drag the point light a little bit upper, and probably we can place the light like the position shown over here. For the other settings, I will recommend that you can follow the settings on the PowerPoint slides. And please do click the draw hollow. The draw hollow. The draw hollow will create a balloon effect around the ball. So this finished the visual representation of our ball. So please be noted that I call this thing visual representation. So from now on, we are going to separate the design into two different parts. The first part is visual representation, and the second part is logic. Okay, please do remember that this is a very important concept. We have to split the design into two separate categories. The first category is visual part, and the second category is logic part. That is because we have two group of people. One is visual artists, and the other is software programmer. So we have to separate as clear as possible for all the tasks in order to balance the loading of the two members in the team. All right, so we just finished the visual part. So this kind of task should be assigned to the visual artist, but now you are doing the same thing because you are a one-man army, so you have to do everything. All right, so this will conclude the visual design. And next, so we're going to write some logic over here. And let me introduce the code over here. We're going to design a mono behavior class. This is the name, example Bob1. So within that class, I'm going to get the light component from the Unity editor and try to turn on and off to tweak the visual representation over here. Do you see that? So if I want the visual representation to be like a lighting bulb, I'm going to turn on the component, which is a light. Just by turning on the light component, it will be looking like a turn on the bulb. And if I'm going to shut down the lamp, the only thing I have to do is turn off the component over here. Okay, so I have to figure out a way to reasonably turn on and off of the light component, right? So that's the goal of the code over here. So we can see that in line number 11, we're going to get the light component, and the light component will be putting the reference, which is P light over here. So in the start code, we're going to get the component in the children game object layer, and we're going to get a light component, just like you see over here. And if the engine do find some light component for us, the engine will return that reference to us, and we can save the reference into P light. So that's the meaning of line number 14. We'll get a one light component over here. And after that, we are going to execute the line number 17 over here. So we can see that within line number 17, within the update method body, we are going to use a huge switch over here. A really, really huge switch. Okay, this is the feature of finite state machine. If you don't know how to use state pattern to make a finite machine, you will get a very large switch. So within that switch, you can see that we write the different logic for different states. For on state, we are going to do the things blah 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 blah. And for the off state, we're going to do the things blah 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 blah. So since we only have two states, the code is not so complex. But if you have 10 different states, the things will get more complex. So this is the huge switch for us. So within that switch, we deal with two different states over here. In line number 19, we are going to dealing with the logic for on state. It's very simple. We just need to turn on the light component, right? So you can see that we just set a true value to the enable field over a p light. So the similar things happen to line number 23. Line number 23 is the logic of the off state. So within that off state, we're going to write a false value into the enable field of p light. Simple, right? Okay, please do remember to place a break at the end of the declaration of a case. Okay, case and the break, they are a pair. Case and the break. And default means if none of the states upward is executed, then the default will be executed. But we don't have any default logic, so there isn't any line within default. All right, so this is the huge switch. And there are some rest of the logic over here. Let's take a look. From line number 30, we are going to detect whether the mouse is clicked or not. If the mouse is clicking the get object, we know that this mono behavior is attached to some get object, right? So if that get object having a collider, yeah, I have a collider, and the script is bundled with it, is in the brother hierarchy, and then the script can detect the mouse click. So if the mouse is clicking the bulb, I'm going to run the line number 31 over here. So I'm going to distinguish whether the state is on or off. If right now the state is on, then I'm going to transition into off. And on the other hand, if I'm under the state of off, then I'm going to transition into the state of on. Simple. And the last one, the line number 39, is a go-to state API. This is a custom API method. So whenever I need to transition my state, I always call this method. So I give it a name, go-to state. So within this go-to state method, we are going to pass one argument to it. And that argument is a type of a state. So what is type of a state? Actually, this type is addressed in the beginning of the code. We use an enumeration to declare the state of this bulb. And we can see that for this state enumeration, there are two different values. The first value is on and the second value is off. And that represents for different states. Okay, so whenever any state is passed to the go-to state method, I'm going to change my state to that target state. So that is it. Okay, if you finish the code, and you can have a test. Whenever you click your left mouse button on the bulb, and the bubble will transition to another state. All right. So I think we can take the rest of the time of this class, this hour, to to make this exercise, right? So well, let's go back on 2:10. Okay, 10 minutes past the 2 o'clock, right? So if we finish the exercise, you can have a coffee break.
Không đúng rồi.
Yes. Okay, welcome back. So if you finish the last example, you'll be able to see whenever you click the bulb over here, you can turn on and off of the lights. So really interesting, right? So what if I just duplicate? With the help of Control D, you can duplicate the bulb for several times. What if I have three different bulbs right now? And let's play the level again. So this time it's very interesting. Any one of these three bulbs could be functional with the help of clicking with your left mouse button. Interesting, right? So no matter how many bulbs you have, each of the bulb could be function, work like a charm. So this is the power of FSM. You just need to write for once, and all of the bulbs in the level should work under the same logic. Okay, great. Next one. And let's make the state a much more fine-grained one. Let's make a fine-grained finite state machine. So let's take the diagram over here before we read the text. So in the previous example, we just implement the body of state, which is shown in yellow color in this picture. But we need an unenter and another unacid method, which is tied to the starting and the endpoint of this state. Why? Because sometimes we have some logic which only run for once. Can you get the idea? Run for once. But actually, the logic you written in last example, this switch will run periodically because it's inside the update function, right? So we know that the update will run for 60 times in 1 second. So this will be the same to the unloaded over here. I mean the line number 31. This line will run for 60 times in 1 second. That is too frequently for us because we are trying to enable this bulb for 60 times in 1 second. That is meaningless. That is nonsense because you only need to enable this light for once, right? The rest of the enabling functions is just wasting your resources. It's just wasting your CPU processing power. We don't need to do that. So for this kind of enabling some things, if you are trying to enable a component or to activate a game object, you just need to run that for once. Get it? So we need this kind of fine-grained finite machine. For some logic which will run for only once, they should be put in the unenter API, or I should call it an on-enter method. So the same thing happens to on-exit when the finite state machine is trying to end for some state and initiate some transition, and sooner or later you are going to be a next state. Then before we leave the state, we are going to call the on-exit method for once. Typically, when we are trying to release some resources like memories, because we are going to live in this state, so we can release some memory, we can release some textures, we can release some files, because we are going to end this state. And if this is the case, you can put the resource freeing task in on exit. So the rectangle marked in dark red color in this diagram is a logic which needs to run for only once. But for the rest of the logic, that should be run periodically. For this kind of logic, we are going to put them in is state. So by reading the first two letters, we can figure out whether this method is for once or for periodically task. So for the is something something method, this kind of method will run periodically. For the on something something method, this kind of method will run for once. So that's the difference in the design. So we can see that in the paragraph over here. So we need a more fine-grained state machine. So we need to separate the original state into three substates. The first substate is on enter, and the second substate is state, and the third substate is on exit. So the below two state, the below two substate is run for once. They are on enter and on exit. So for the periodically run forever, it is state. All right. So for the next example, we'll see that we are going to put the logic which just need to run for once in on enter. Great. Next. So before we reorganize, before we refactor our program, we are going to make a new structure. It will be like this. The first thing is to declare a boolean, also called a bool, and with the name of trigger enter. We're going to use this boolean flag, flag, F-L-A-G, flag. So what is called flag in software engineering? A flag would be some notifier, and typically they only have two states, 1 or 0. So by simply using a little flag, I can know the status of some something like a very important information. So in this design, I'm going to declare a boolean flag, and the name of the flag is trigger enter. So the name of flags is coming from the electrical engineering field. So if you are familiar with embedding system, the term flag is used very often. So we just borrow the idea from electrical engineering, from the embedded system design to this game design. Okay, so whenever I enter any of the states, the first thing is to figure out whether the trigger enter flag is set or not. If the trigger enter flag is set, that means this is the first time we enter this state. So we have to do some on enter logic in here. And whenever we process all the on enter things, we're going to reset the flag back to false again. And the next time we enter the on state, the trigger enter will be false. So the on enter will never be executed again. So that's the idea by using a simple flag to implement the onEnter. So we see the step number 4. Whenever we transition from some state into a new state, at the end of the transition, we have to set the flag to true. That means when the new state is executed, uh, we have to make sure the trigger enter is true so that the onEnter will be executed. So that's the idea of using this little flag. Okay, great. So after we modify the structure, we're going to implement several onEnter logic into the corresponding part of the code. So we can see that the new line number 18, So for this line, previously we used this line to turn on the visual part. We used this line to implement the visual representation of turning on the bulb. But just like we analyzed before, this should be done for only once. So we embrace the whole code into the trigger enter flag. And the same thing happened to line number 23. So in line number 23, we're going to turn off the visual representation of the bulb. So this thing should be done for once, and that's why we put the code into the condition trigger enter over here. And please do remember to reset the flag back to false. Actually, I should do this twice in each of the onEnter, but I'm a little bit lazy. So here I just do for once. I just reset the flag only once here. And we can see that in line number 43, we set the flag to true whenever we end the transition. Okay, this is important because from now on, our following exercise will need the help of onEnter. So before we write more logic into the onEnter, we have to make the structure it is error free. So we need to finish page number 12 before the following exercises. So here we are going to spend about 5 minutes. Let's spend about 5 minutes to finish page number 12. Okay. Okay, let's go back to the lesson. Wait a moment. Switch back to the uh, only one screen. Yes. Okay, so this should be the same responses what we had in the last exercise. So nothing changed. The only change happens to the processing power because right now the regional representation is updating only for once whenever we enter some state. So that's save a lot of processing power for us. Nice. Okay, next. All right, so here comes a little bit complex situation. We need to introduce a new state, which is called a broken state. So we see that there isn't any bulb can be last forever. Most of the bulb has a duration. We know that. Probably for this bulb, it can sustain only to be turned on for 3 times. The fourth time you are trying to enabling this bulb, the bulb will crash. The bulb will broken. All right. So that is a very expensive bulb, you know. So just kidding. All right. So this will be the updated finance state machine. Whenever we trying to enable the bulb, we are going to distinguish whether the bulb has enough health point. Yeah, a bulb has a health point, just like an enemy. So, for example, if the bulb has a health point of 3, and for each time you enabling the bulb, you will just deduct 1 point from the HP. So, if the starting HP is 3 and you are turning on the bulb, and the new HP of the bulb will be only 2 points. 1 point is consumed in the enabling process. If we are going to turn off the bulb, there isn't any consummation of HP because turning off is a very easy task. So we are not going to deduct any points from the bulb. So the second time you are trying to turn on, the HP will turn in from 2 to 1. And the third time you are going to turn on, the HP will will be from 1 to 0. And the fourth time you are going to turn on this bulb, no, this time your HP is equal to 0. You can fulfill the condition to transit the state. You are not allowed to transit in this path. On the other hand, you will be allowed to transit your state through this path. Let's take a look at the condition over here. This condition is addressed that when the bulb is touched and your HP is less or equal to 0, then this path is allowed. So you'll be allowed to transit your state through this path, and this will lead to the broken state. Boom. So this is our new finite state machine. Can you get it? All right. So the first important thing is that I need your help to understand every detail on this diagram. All right. So the first thing you have to do is to understand any information on this finance state machine, because next time you are going to draw this kind of diagram for the project and deliver to me. So in your midterm project, you are supposed to draw similar FSM diagram for your design and include it in your delivery and send to me. All right. So this is the first thing. You should be able to draw the FSM you want. And the second thing is, Mr. Fu, how to turn this diagram into codes. That is very simple. This is the code. This is the code. And this is the diagram. We separate the things into 2 categories. The first category is the visual representation, and the second thing is the logic. Do you remember? So you see that the next page, we are going to deal with the visual representation. We are going to make a two material. Sorry, we're going to make a new material which will be look like a black material. And whenever the bulb is broken, we just put the material onto the surface of the bulb. So this will pretty look like a broken bulb. Simple. Okay, we finished the visual representation design. And next, let's go back to the logic design. In order to introduce a new state, we need to add a new value into the enum. And we're going to call this new state of enum broken. It's like this. So next time, if you are going to introduce more state, that is really simple. You just need to append the values over here. Next, since we had a new state, the switch will grow. Definitely it grows. So you can see the logic for broken state is addressed over here. And of course, for the broken state, it also implements some unenter logic. So we see an unenter logic over here. And all right, I should place some red box on this code diagram, right? Okay, let's mark the update paths on this code. And besides that, we need to provide two material. And furthermore, we are going to implement the HP and the mesh renderer. Of course, we need to initialize uh, the mesh renderer and the health point. And we see that we modify the code because we set the material in each unenter. All right, anything else? Oh, yes. And in the mouse down, whenever we press the mouse button on a ball, we're going to figure out whether the health point is enough or not. If the health point is enough and the value is greater than 0, then we'll deduct 1 from the health point and go to on state. Otherwise, we are going to do nothing and go to the broken state. Okay, great. And the last thing is about dealing with the visual representation. It's called changing the material. So we set up a method called change material and pass the one argument which is of a type material. And all right, from line number 71 to line number 73, we just get the array of materials from the renderer, and we only change the 0th material to the target material and write back the whole array back to the mesh renderer. So somebody may ask that, Mr. Fu, this is too tedious. Why don't we just update the zeros element of the materials array? No, Unity prohibits you to doing so. So the only way for you to change the zeros material of materials array is to read the whole things out and modify the zeros element and write them back. I know this is complex, but this is provided by Unity. It's Unity asking we to doing things like this. All right. Okay. So for the path marked in red, I need your help to implement in your code. And let's take about 10 minutes to finish to page number 18. Okay. And you should see your bulb is right now sometimes it will broke if it lights for more than 4 times. Okay. Okay, before you try the bulb, please do remember to assign two material for each of the bulb. So we just public two materials in the script. So we need to assign a material normal and a material of broken. So for the material normal, and let me show you my screen. So just like you see over here, we have to assign two different materials for the new script. Each is a normal material and the other one is a broken material. So for the normal one, we're going to assign the glass material, which is extracted from the FBX glass. This is a normal material. And for the broken material, you have to make your own. So for me, I just add a new matte broken material which is having a black color only. That is the only differences from the default. So let's play the level. So for this time, you'll see that whenever you lighten a bulb for the fourth time, the bulb will be broken. You don't have to remember how many times you had to turn on for any of the bulb because it will calculate the times automatically for you. Oh, I may forget to initial the state of each of the bulb. So in the start, I think we should set the state to off in the beginning. Otherwise, it will have some problem. Okay, for the student who finished the exercise, you should be able to move on to next page and to have a glance in in advance because we're going to fix the bug. So if you finish the exercise, you are encouraged to think about how to make a solution for this problem. The problem is now we are going to fix the bug. Whenever we press F, the F of fix, the first character of fix. Whenever we press F, we hope all of the broken bulb could be recovered again. That means all the broken bulbs should go back to the off state and with the refilled HP. The HP should be refilled to 3 points. So how to do that? Mhm. So I will introduce how to do that in 2 minutes later. Okay. So but before that, I think you are encouraged to think about how to solve the problem by yourself. Oops. Okay, so go past the problem and solve the problem. Okay, probably you already had a rough idea, or you even solved the whole problem. Okay, the answer is that the first thing for us is to update the finite state machine diagram over here. So although you already know the updated figure, but you can pretend that you didn't see the figure over here yet. All right. So next time you'll get only a task description from your designer partner, and he or she may be saying that, hey George, please make a new function for me. I want the bulb to be fixed whenever I press F. So you only get the request or requirement in a form of text or paragraph or some similar, some simple sketch. But your duty is to turn the idea into state diagram like this one. So we think that whenever we press F for the keyboard, and we should find the broken bulb and transit all the broken bulb into off state. So this is the new transition we add into the diagram. All right, this is a good solution, but how to implement that? Next. So we decided to add some new lines of code to detect whether F is pressing or is just pressed. And if F key is just pressed, we go further to figure out whether the state is underbroken. So if a bulb having its state underbroken, then it will execute the line number 58, and it will refill its own health point and go to state off. Great. So each of the bulb will judge whether the condition is met separately, and we don't have to filter out which bulb is valid to transit, because each of the bulb has its intelligence individually. And another question would be like, Mr. Fu, can I put the input detection within the on enter or the is state logic codes? I think most of the tutorial online or all the textbooks I can bought from bookstore, they are all doing the same things. They all put the input detection lines in the logic, in the state logic or on enter logic. Can I do that? Okay, I suggest you never do that. That is because in the future, your switch will grow to an enormously large extent. This switch, I mean, uh, this one. As you can see, right now we just have 3 states, right? But if we are going to use the finite state machine to make a character, probably 10 state is a common thing. 10 states. So you have tons of code in a switch. And whenever you insert one line into it, you'll never find it again. You don't know there is a line 1 month ago. There is one line is detecting the input. You will never remember this thing 1 month ago. So if you forget about you put such a line, and in the future you'll see some weird, very weird behavior of your character because you forget where you inject the input code. So my suggestion is that for all the input things, you extract the code outside of the logic and put them separately in order for you to have a higher possibility to find the code quickly. Sorry, let's go back to the well, this is the diagram part. All right, so what we can see from the screen is that we put the input detection outside of the huge switch, and later 1 month later, if you see some weird problem that is related to the F key, you will quickly find the part over here because it is outside of the switch. Every key detection will be put over here, and every mouse detection will be put over here. They are very clear for all the designers. So that's why we extract. That's why we extract the input code and put it over here. All right. I hope this will be benefit for you. And let's see the code. If the F key is pressed and the bulb is in broken state, then the bulb is going to refill the HP and go to off. Right? If you finish the code, you will see that I'm going to going a quick fix over here. It's over here. If input GKD and the F key. So if the state is state dot broken, then I'm going to refill the HP and go to state dot off. All right, I just finished the logic and go back to test. So let's see. Yeah, the bulb is broken. And let me press F. So whenever I have a broken bulb, I can press F to fix all the broken bulb. Interesting, right? All right, so if you finish the exercise, you can take a 10 minutes coffee break. Okay, so let's go back 10 minutes later. Okay, welcome back. So in the previous classes, and we know so many things about how to make a design pattern, and probably we had used the strategy pattern and the state pattern before. No, did we use state pattern before? Probably okay, probably yes or probably not. But in the following hour, we are going to explore deeper into the design pattern. So we're going from the switch type design into the design pattern design. So we are going to introduce the state pattern over here. Actually, I may not have enough time to elaborate the detail of strategy pattern and the state pattern. And you are encouraged to find the detailed online or read the book in the GAN 04. Is the book over here, I think GOF, design pattern. Uh, so let's find the book on Amazon. Okay, this is the classic one. You should have one. No matter the real book, the paper book, or the ebook, either way works. Either way will be great. I think you can even find this book in the library in NTUT, and probably you can get some PDF online, but I'm not sure because this is a really classic and traditional book. And when you are learning the OOP, the object-oriented uh, programming, probably in your first year or second year, at that time, your teacher may introduce this book to you. So today we are going to take two design patterns from the book and introduce to everybody. That is, where is it? Sorry. State pattern, sorry. Okay, we are going to use the state pattern to remake everything. And we are going to exclude all the switch design previously and renew the whole design with the help of state pattern. We're going to skip over here. All right, this is the one. Okay, you can read the task when you back to home. But right now, I'm going to introduce the UML diagram. Did I introduce UML diagram in this class before? Yes, in the chapter number 4. Okay, this one. All right, if you have less idea about what is a UML class diagram, you can go back and refer to this page. This is in chapter number 4, 404. And at that time, we introduced the inheritance. It should be a white and hollow arrow. and we introduced the aggregation and composition with diamond end, solid diamond end, or a hollow diamond end. The solid diamond means the owner class should take responsibility to create the children class, and the vice versa. And if this is a hollow diamond, that means the owner doesn't need to take responsibility to create the children class. All right. So let's go back to the diagram over here. Uh, this one. Okay. This is the most complicated idea in this lesson. Okay, let's start from the abstract class. It's over here. We have a state class over here. And the state class only have one method, which is called the handle. So every children of the state class must implement handle. And they have different logic in the handle because the state represent for different logic states. Sorry, different state logic. And if I have an on state, and I may able to call the class state on, and because this is a concrete logic, what does it mean? What is concrete logic? A concrete logic means the logic fully represent for the business logic. It could be utilized directly into the system. It's not trying to represent something. It's the real body. Okay, so we have a concrete state A, namely the state on, which is inherited from the abstract state class. And we also have a concrete state B, which might be state of, and the state of will be the children inherited from the abstract state class. And this is a very, very nice structure which can break the huge switch loop and into several pieces of C# code. So this is what we expect in the beginning of this lesson. And now let's see the left-hand part in this figure. We have a context class which represents for the client logic. Okay, so maybe you never heard client logic before, but in the software engineering domain, a client logic is the business logic, which is the you can take this as the main logic in the game. All right. Whenever I say client logic, I mean the main game logic in your game. So our client logic will own a state, but we are not sure whether either the on state or the logic or the off state will be owned at any moment. But since this is a state, we can call the handle member method. So in the processing code, in some line, we're going to call the handle, but right now we are not sure which one we are going to call. So this is the flexibility we gained from the design pattern like this. The only thing we are sure is that the state reference must have one handle method to be called. But right at this moment, we are not sure which one will be the exactly one. It depends on the operation. When I get on state, then I can execute the handle of an on state. If I'm getting a state of all state, then whenever I call the handle, I will execute the handle logic in off state. So this gives me a really big flexibility to change the logic content. All right, so I just turned the figure from the GAN 04 from this is the original figure, and this is my figure. This is my FSM diagram. Sorry, the class diagram. This kind of diagram is called class diagram. So if we are going to apply for a software engineer job, then you must be able to draw class diagram. Otherwise, you will not get any chance to enter the company. All right. So for me, I'm going to implement an object class. I'm going to call this class an I state. The I means interface. Somebody say that, Mr. Fu, I heard that when you are going to declare an interface, you should use the interface as the type of this class. Yeah, you're right. But for me, sometimes I prefer to use an object class as an interface. This is my personal hobby. You can use your own hobby, but for me, sometimes I prefer to use abstract class as an interface. If you ask me when is the chance to doing so, please take a look at here. In this I state, I have a member reference called machine, which having a type of machine. Do you know that the interface in C# can have any member reference and can have any member variable or field property, something like that? Do you know that? Interface is not allowed to having any member variable. No, no way. Only abstract class can have member variable and member properties and member reference and similar things. So that's why I'm using an abstract class over here instead of an interface. So can you get that? All right. And let's see that this is the parent class. It defines, it has a machine. Okay, what is a machine? A machine is actually the client logic. And it has a constructor, in short, CTOR, constructor. And whenever we construct an instance of this class, we have to provide a machine in order to save to the member function. Actually, you may never instantiate an abstract class, but this regulates the children of the class. So the children must to implement the constructor and in this signature. All right, so we see that we have two children class. One is state on and the other is state off. So they all have their own constructor and they all have their own on enter, is state, and on exit. Oh, there shouldn't be this line. Sorry, I should delete this line. All right, so let's see the client logic. Our client logic is inherited from mono behavior, and we have a state. We just know that we have a I state. See, we have an I state, but we are not sure whether the I state is state on or state off. Unless we run the program, otherwise we are not sure who is the real class, who is the concrete class of this I state. All right. So next we are going to declare a trigger enter just like before. And we have a start, we have an update because we are a mono behavior. And we also define a go-to state. And the go-to state having one argument, which is the next state. And we also have an init, which can init the whole context for us. All right. Probably you are not so sure what you are doing right now, but pretty soon you'll implement everything. Okay, this is the first time you are going to use the state pattern to implement your finite state machine. I think we can take 15 minutes to doing so, but we have to do it quickly. All right, let me introduce the reference code. The first thing is to declare an I state abstract class like this. We need to having an instance pointing to the referencing to the client logic. So we have a like this. We have a variable machine like this, and then we are going to declare a constructor. The constructor doesn't have any return type. So see, do you see that in line number 9? the declaration of the constructor doesn't have a type of return. Originally, we should put a void over here, right? But since this is a constructor, you never put anything, any type over here. So including a void. So you just need to put a public over here or a private, okay? It depends on the design pattern you implement. So whenever we construct an I-state, we have to provide a machine. And whenever we get the machine, we just write the machine into the member variable, okay? This is an initialization. And we just trying to log something to indicate it's calling the constructor right now. And then we see from line number 15 to line number 17, we declare 3 abstract methods over here. So Mr. Fu, what is the abstract method? An abstract method means it doesn't have any body. It's the duty of the children to implement the concrete body. This is the abstract method. So can I call an abstract method? No, you're never allowed to call the abstract method because there isn't any body. So you can try to instantiate the abstract class and you'll get a compiler error. And you can try to access the abstract method of the abstract class, you'll also get a compiler error. The compiler will prohibit you from doing so. Okay, okay, that's the idea about abstract class. Next, we just implement the I state. Now we're going to inherit from the I state. The first state we're going to implement is the state on. So as we can see that we declare a class which is having a name state on, and it just inherited from I state. And we just implement the constructor for the state on. And you can look at the line number 7. We declare a constructor having the same name, which is state on, and we should pass an argument which having a type of machine. And what is this? This means we are going to call the base constructor. Who is the base constructor? The parents constructor is the base constructor. All right. So whenever you call something from base, the base meaning the parent. Here the base is the I state. So that means for whenever we call the constructor of state on, we are going to call the base constructor and just pass the machine to it. All right. And after we call the base constructor, we can do something, but obviously we didn't do anything over here. We keep it as a blank. All right, this is the children's constructor. If you can understand, you can memorize everything temporarily. So for a basic designer, you're never going to change the line like this. You can maintain any children constructor like this. And when you get familiar to the structure, you're having to grow some code into the curly braces over here. All right, so next, let's see the 3 methods over here. So for the on enter, we are going to override. Why here we are going to override? Because it was the abstract in the parent. So since it was declared as an abstract in parent, you have to override. If you're missing the override keyword, your compiler will send you a warning message saying that error message. Sorry, your compiler will report an error message to you saying that you should override the abstract class, the abstract method. Sorry. So we just do a debug log message in it, and we are doing the same debug in the in the is state and the on state too. Please do remember we have to put the override again and again. For these 3 abstract methods. Great. Next. So we are temporarily skip the state off because the issue having the send logic to the state on. We are going to try the client logic ASAP. So here we see our client logic, which is defined as a class of machine. The machine inherits from mono behavior and is having some I state. I don't know what kind of the I state it is right now, but later we are going to figure it out. Okay, let's do the following things. So in the line number 11, oh yes, here we instantiate a state on and we pass ourselves to the constructor. Why are we going to pass ourselves to the constructor? Because you declare that. Did you remember? You declare the constructor should having one argument which is having a type of machine. So here, when we instantiate the state on, namely calling the constructor of it, and we are going to pass ourselves as the machine it needs to here. And then we'll get an instance of a state on. We're going to save the instance to this reference. Wait a moment, Mr. Fu. Here, the class is state on, but here the reference is the I state. Can I save a state on to a I state reference? Yes, you can. This is, do you remember Salim principle? The children can be taken of its parent. All the children can do the things his parent can do. The children is much powerful than his parent. So this is one of the solid principle. Uh, the L, I don't remember the exact Liskov inversion. All right, so we generate a children and take it as its parent because the children could be taken as a parent and do everything his parent can do. So we just saved it to the state. And the next, whenever we update the logic, we call the is state, which belongs to the state reference. Okay, that's it. So let's do the same arrangement. We put a ball here and we assign the code on it. And we should be able to see the log messages over here. Phew. So it's a long process, right? So now let's take about 10 minutes. Let's take about 10 minutes to rewrite everything from page number 26 to page number 29. Okay, 26 to 29. Okay, I'm sorry, we are running out of time, so I have to introduce the idea in this chapter before. So you may take some times when you're back to your dormitory or back to your home, and you have a better idea about what is going on uh, by the state pattern and using the FSM over here. So that means you probably will not be able to run all the examples in this lesson. If you spend more time, you'll be able to finish all the exercise over here. So let's see the framework number 2 over here. All right, probably you will spend some times when you back to your dormitory and you are encouraged to run all the exercises in this PowerPoint slide. So let me introduce what's going on in the framework 2 exercise. So in this exercise, we are going to add another state, which is state off. And we are going to implement the state toggle by pressing the T key. So previously, we were toggling the verb by clicking the mouse button, but temporarily it's a little bit hard to doing so. So we make a workaround. We just press T key to toggle the state of a verb. So that is really simple. The first thing is that we have to modify the state on design, and the only thing we are going to do is to find the is state of state on, and we are going to deal with the input message. We are going to deal with the get key down of input to distinguish whether T is pressed or not. If the T key is pressed, we are going to call the go-to state to transit the state. But where is the go-to state? As you can see that there isn't any definition of go-to state. So where is go-to state? All right, take care. This time, we implement the go-to state in machine. Because the transition should be a function of FSM machine, it doesn't belong to each state. So the transition things should be described within the scope of machine. So you'll see that we update the code of machine. We just implement the start, we just implement the update, and we implement a new method called go to state in machine because we think this should be a function belongs to machine. So the rest of the code will be pretty similar to the switch version. We pass an argument of I states. Also, we don't know which is the concrete state right now, but the children could be taken as a parent. So we just we address the argument as parent. So later, some children will pass to replace the current, to replace the parent. So whenever we get a new state, the first thing to do is to distinguish whether the current state is a null or not. We just place the question mark over here. The question mark means if the variable is a null, it will be terminated at the position of this question mark. It will no longer execute any code from here right after. So the program will stop at here. And it will prohibit the error message generated by the compiler or by the runtime when you execute the program. But if the state variable is not null, the question mark will allow the execution to be proceeded, and the following code will be executed. We are going to call the onAxis of the state. All right, since it's a children of I state, so it must implement the onAxis method. Why? Because it's an abstract method described in I state. So all the children should implement a concrete content, a concrete body of onAxis. So we just execute the asset. And then we are going to transit the state. So that means we are going to override the state with the new target state. Simple. And after we transit the state, we are going to set the flag to be true, just like before. So the trigger enter will be true. So this is the new go-to state. And for the rest of the code, we're going to go back starting from the above. Line number 6, we just declare a trigger enter. Yes, And in the beginning, we are going to initialize the states. This is will be like before, but this time, instead of directly assign who is the reference pointing to, we just call the goto state to transit to a new state. And in the update, just like before, we are going to detect whether trigger enter flag is set to true. If it is, we just call the on state enter. Sorry, we just call the on enter. And after the on enter is finished, we just set the flag to false. And in line number 18, we just call the periodic is state function, just like this. So this is the structure of our finite state machine. And let's go back. So we just write a new state of, and we just detect whether the t is pressed down in the is state. If it is, we just change to another state, which should be a state on. All right. So I'm sorry, we just don't have enough time for this exercise. But before the end of this class, let's introduce more exercise content, okay? And you can practice by your own. So the next framework is to make the context class. All right, so we just implement the I state and state on and state off and the finite state machine. And actually, all the dependencies should not belong to machine. What is dependency? All right, this is dependency. The point line. Did you remember that we get the point line in the previous code? All these kind of GAN elements within this level shouldn't be known by the abstract logic we written for the on and off. Can you get it? The on logic and off logic, they are abstract logic. They didn't know the component, they didn't know the mono behavior, they didn't know anything within the level. Because some level designer places this kind of GAN element, but we are programmer. We don't know which is the real instance the designer plays into the level. So this kind of dependencies should be taken consideration by a dedicated class. We call this kind of class content class. All right, so that just like you can see, for the member variable parts, only the context bulb class, it has the light component, it has the mesh renderer component, it knows who is the normal material and broken material, and it also has a variable of health point, and it also has some events and other classes. So all these kind of dependencies is pushed out from the framework and into a dedicated class. We call this class a context class. And the context class is taking responsibility to initialize all the dependencies. And it can deal with the dependency like change material and deal with the dependency like turning on and off the lights. So all the dependencies things should be taken in this class. So let's go back to see the original classes. There isn't anything related to the Unity GAN level right now. See? All of these things are designed by our FSM concept. So we roughly separate the whole package into two things. One is something dependent to the level. The rest of the code is independent to the level. So this is it. Okay, so if you can understand the idea, we're going to create, modify the machine code and push out all the dependencies to the context class. Where is the context class? Oh, here is the context class. You will see so many Unity scenes in here. And whenever you are going to deal with the Unity scenes, and you can call some method bundled to this context class. Right, that's its idea. And this time you can press T key to turn on and off. And the next example is to implement a new state. We are going to implement the state broken, and this is pretty simple. You just create a new class which inherits from the abstract I state. And by following the same rule, you can implement the code. You just need to take care of the is state or the broken. And for the context, for the initialization, you have to init the HP value. Okay. Right. So you can have a broken code. And then you are going to implement the fix, the broken fixing function. This time we are going to press R to replace, to repair all the bulb. So this is simple. Whenever you press R key, and all the stay broken bulb should recover from the HP and transit to an old state. So this is the corresponding part for the on and the off and the broken. And simple. So very soon we can fix the bug. But how to enable the touch toggle? Originally, we are touching the bulb to switch the state. But right now, how to do that? All right. So do you remember the structure, the event center? This should be addressed in chapter number 3, right? At that time, you create an event center and an event subscriber and publisher. So in the original GOF design pattern, this is called the observer pattern. And the GOF makes these two things together. So in the original design, there are only two rows in this design pattern. But I personally split these two to separate rows. Okay. So this time we are going to do the same thing for the mouse clicking function. Sorry. Oops, where is it? So we are going to let the context to hold an event center. And then we are going to make another new class for sensor. Actually, this is a collider bundled to the bowl. And whenever the sensor sends the mouse clicking event, it's just a call by direct binding. You just call the event center. And the event center will invoke the corresponding event. So it's the duty of the subscriber to subscribe to the center what should be the response whenever somebody is clicking the ball. So this is the structure of the whole thing. So if you can see, there are two mutual communication among these three different rows. For these two rows, they are connecting together through direct binding, through direct method call. That means these two rows should know each other. They should keep the reference about who is the destination of the call. So this should have a double binding before the call. So we will introduce the idea. And for these two rows, they communicate together through event system. They are using the Unity event. So of course, you can switch from direct binding to Unity event. We introduced 4 different methods to mutually exchange message, right? In chapter number 3. If you forget about that, you can go back and see the chapter content. We introduced 4 different methods. And here we pick direct binding for these 2 rows, and we pick Unity event for these 2 rows. All right, great. So the first thing is to make a sensor. So the sensor class will be like this. So according to this design, the sensor should know who is the event center. So that's why we put a context over here. Actually, the event center is a context. So whenever the sensor finds the mouse is clicked, it just call the event center and triggers the event touch event. So direct call. All right, so we just finished the design of sensor, and next we are going to introduce the code for the event center. So we see that the event center will be implemented in the context, and it's just holding a Unity event over here. And the most important thing is that here we need a double binding. The double binding means the sensor knows who is the context, and the context knows who is the sensor. See, the context knows who is the sensor, and before the sensor knows who is the context, so that they can code mutually together. This is called double binding, and this is required for direction method code, direct method coding. All right, so you should assign or get component to find this sensor so that they can trigger together. All right, next, for the state logic, whenever the on enter is executed, that should hook the action to the event center. So like this, and we write a mouse down in the state on, but since this state is not inherited from the mono behavior, the on mouse down will not trigger automatically. So the purpose we give it a name, the send to the Unity API, is because we hope you can remember quickly. We are going to hook this method to the event touch event. So you can see that we just hook the on mouse down to the event touch as a listener. So we are doing the same thing for the state of, and the logic will be the same. And please do remember remove the listener, just like we introduced before. Okay, everything is bundled together and everything works properly. Now you can click the bulb to turn the state. So this just understand what it is and just implement this figure into the code with the help of the idea event center we introduced in chapter number 3. Do you remember? If you forget what is event center, you can go back to chapter number 3 and review the details. And then making a framework. Okay, so this is an advanced skill. If you know how to package DLL, then we are going to package the whole thing into a DLL and make it a library. Or you can publish as a plugin to sell it in the internet. So just like before, we have these kind of classes. But this time, we are going to make a parent class for the context ball. We are calling this parent class an I context. So again, we are going to use the object class to implement the I context. The I context just need to implement one method, which is called init. Okay, if you do these things, you will see that all the red circled part of the class are not related to any dependencies in the game level and are not related to our client logic. See, all the client logic is pushed out of the boundary of the red line. So the things within the red line will be compiled and keep as the DLL, and you can call this kind of code a framework. We'll never modify any line of the code. We'll never change any line of the code further. This is a stable code. And if you package all the things into a DLL, next time you're going to modify the logic, you can inherit some classes from the package. And you can implement your custom logic. You can implement your custom dependencies. And finally, you can implement another client logic to control everything. So this is the idea of framework. I'm sorry, I might not have enough time to talk about how to make these things, but everything is listed over here. By following the steps, you can finish the framework. All right. Okay. So if you really want to learn the framework, I highly recommend you follow all the steps after the plot behind. Okay, and but if you are a visual designer, you don't need to you don't need to do the following exercise. If you only care about the visual design, you only have to understand the switch type FSM. All right, and you can finish your midterm project by a simple switch, but that is very huge part of code. But never mind, because you are a visual artist. Okay, but if you are designed to be a software programmer, then this diagram you must understand, and you must implement each detailed code in this class diagram. All right. Of course, if you implement every line of this code as your midterm project, you will have a higher grade because this should be compatible to the project number C. This should be an RPG battle, right? And for RPG battle, I think you may consider to use this kind of structure to finish your project. All right, that's it. Any question? Okay, if you have any question, you're welcome to find me, and I will do my best to explain every detail to you. And I hope everybody can finish the midterm project. If you have any problem, please welcome. You're welcome to ask your and provide your question to me, and I will respond to you ASAP. Okay. All right. So happy developing. See you next time. See? 哎，要等我。哦，是哦，哦，对不起，你要什么课？哦，哦，好，好，我马上让出来。目前，这样在扣，就编导开始，然后我就现在设定是2个，然后一开始就可以先选大，然后选完大图以后就是大项，然后就会看那个，它这里就有一个大分寸，然后这里就是会有公式因素，然后这边是每一个人的回合会做的分数，对，然后之后回到 round，这应该是因为其实我们有2种设计方式，一种是全部用 finite state machine，另外一种的画流程图。你以前在学程式的时候，老师应该会要求画流程，那个是没有 state 概念的，那就是一个从头到尾，然后一直跑。没有，我是目前这个弄完以后，对不对？我只是先确定好，大概会把它再弄完。好，如果是这样的话，我觉得非常非常丰富。OK，应该是很精彩的吧？应该是很精彩。虽然我没有实际想象跑过一遍，但是我看这些状态跟它的条件流程应该是很够了。对，但是通常该怎么说呢？在波态的时候，我们不会做效果，但是就是比如说进来的时候，你要一个转场或者是什么特效，有时候为了实现这些特效，反而会让你的结构生出非常多的状态出来。不过在这一次里面，如果你想要试试看，在转场之后加特效的话，你可以试试看。然后你就会发现用 FSM 做要非常多那种小状态。进到这个小状态，然后播放特效，特效播完之后再进到真正的逻辑状态，那会很过瘾。我只能说，我之前用的，我是做那个东西算是，我之前做的那个它的状态。如果你没有用状态的话，它就很容易抽筋。就是这样的流程，你要不用状态继续做，它就很容易会你输入点没有想清楚，或者是你加了没改，它就很容易会抽筋。这是我之前然后我确实很好啊，你已经有做状态的概念。 这是什么？你直接用，
我用，
这是你们自己的框架吗？
这是我们同学做的框架，然后我直接做了一个神魔之塔。那它是沿用学长。对，我这一整个东西它是可以正常动的。
很好。
对吧？我确实有那个黑白，其实你原本是想找引爆核实的那个特效，但是找不到。
那边要加特效，
干脆直接黑白特效。我那个是直接让我夺印盒是直接让它播放完毕，它才可以执行下一个动作。
这件事情就很烦。
对，因为这个东西你就不可以用很多条东西一起跑那种感觉。
对啊，
应该说
如果有人在那时候很急的按的话，通常会出问题。
我在那边就没有给他设定，就是他在那边还能再输入东西。
就这种很细节的东西全部上，就是播特效的时候不准输入，然后特效完了又可以输入，然后特效要怎么放，这就很烦的事情，对吧？
那个我之前已经搞过一次。
哦，想必这边你应该是明白的，但是要做到漂亮就要
我这次想要高出全程用上面的规则来。
你试试看，把你的 code 可以 combine 成 DLL 部分，你就尽量抽，试试看。那如果你可以明白这件事情的话，你就等于是真正理解这些 pattern 为什么要这样做，然后你第二次做游戏的时候就可以。
对啊，因为我们第一次，这算是我们第一次做，然后我那些想法什么的，全部都是先根据我那同学他在原本的框架里面，可能有在他的系统的最背景的部分做了一些事情，我就看着他那个背景部分，慢慢的摸那个他的一整个，把它摸成那个。
哇，还要做那个什么叫三消的地方就要花一些。
不过说真的，游戏机制反而没有后续很多玩法来的麻烦。反正游戏机制我花2个礼拜全部完成，整体上还行。好，
好，再做一遍。OK，see you，拜拜。
哦。